Welcome! In this video, we will continue our efforts to determine the ground state energy of helium. Now, we know that theoretically, that value, or actually what is measured in experiments, is minus 79 electron volts. So we would really like to get close to that amount. Now, in the previous video, we didn't really get all that close. Our wave function that we used as the trial function, it didn't really account for the interaction between both electrons. We simply said, okay, we have two separate hydrogen atoms, and we really didn't take the interaction into account at all. So this time we will do it, and we'll see that that's going to actually improve our result. So let's consider the situation again, and let's think about it. What wave function could be picked as a trial function? So we have helium, which is basically two electrons orbiting these two protons, right? Nobody cares about neutrons here. So last time we said, okay, we have these two separate electrons orbiting basically a hydrogen atom, but with a bigger z, right? That's what we did, and with a z equal 2. But the thing is that if we have two electrons orbiting, then they will partially block the potential from each other. So this is not a one-by-one analogy, but think of it like this. So we have the nucleus. Actually, maybe I'm going to draw it. So maybe we have the nucleus here, right? The protons. And if we have an electron here, for example, and then an electron here, then the electron that is further back, it doesn't really see the entirety of the nucleus because it's partially obstructed by this electron right here. So this is an effect that we call shielding. And this means that basically what the nucleus sees, it isn't quite two electrons. Not the entirety of the charge of the electrons will be felt. So for that reason, the effective amount of electrons is going to be less than 2. More than 1, of course, but less than 2. So for that reason, what we want to do is use basically the same wave function that we used before, but this time allow for that liberty. Okay, so let me show you what I mean. So our trial wave function that we used last time was this thing, R1, R2, and then we had 1 over pi, actually I think it was 8 before. We had 8 over pi a cubed e to the minus 2 R1 plus R2 over a. Okay, but this time we have a different situation. Previously we said, all right, we just have these two electrons, blah, blah, blah. But we don't really know how much charge the electrons are going to feel coming from the nucleus. We don't know that. So for that reason, we won't just say, all right, z is equal to. And that's what we did before, right? We put z equal 2. For that reason, the value for a changed, and that's why we were left with this 2 and this 8. So now let's just leave z be. Let's just say, all right, this is our variational parameter. And at the end of the problem, once we find the energy, we will minimize this parameter so that we can minimize the energy. So now instead of having this 2, what we will have, and once again, as a quick reminder, just as we did in the previous video. So the Bohr radius, this is 4 pi, I'm copying it right now, h bar squared, the mass of the electron, e squared. So the point of this is that it depends inversely on the charge, right? But this is, of course, I mean, that formula is thought for the case where we have hydrogen, right? Where z is equal to 1. And in the previous video, we already included the change z equal 2. But now we have z in general. So these e, it is squared because 1 e comes from the electron and 1 comes from the proton, right? From the proton. So now the one that comes from the proton is not going to be just e, the charge. The charge will be ze. So for that reason, we will have ze. And then, of course, the e from the electron that has not changed at all, so it will be squared. So the important thing to note is that the new a is the old A, but divided by Z. So the same logic that we used in the previous case, in the previous video, but this time it's a Z instead of a 2. So everywhere where we had an A, we will now have to divide the A by Z. So in this case, it's going to be multiplying, and here we get A divided by Z. Last time we had a 2, that's why we had 2 cubed, which was 8, and now we have Z cubed. Okay, so that is what happens. If you are unclear, I took a little bit longer to explain it in the previous video, so maybe you can check there, but that is the idea. Right, the Bohr radius is now changed since we are no longer in the hydrogen atom. Now, what is the Hamiltonian? The Hamiltonian is going to be the same as before, actually. So minus h bar squared over 2m, and then we have, this is the kinetic part for each one of the electrons. And then we have the Coulomb interactions of the electrons with both of the protons in the nucleus. So we get 2, right? There's 2 protons over R1 for one electron, 2 over R2 for the other electron, and then we get the interaction term, so between both electrons. So plus sign, of course, because minus minus, it gets plus. And then we have 1 over the distance between R1 and R2. Okay, now this is what we had before. Now, if we were to naively go ahead and just take the expectation value of this, we would find that we get the exact same thing as before. So this will simply be 2 times the, basically, because this Hamiltonian here is one hydrogen atom here, except that it has Z equal 2 instead of Z equal 1, and one hydrogen atom here, except that it has Z equal 1, Z equal 2 instead of Z equal 1. So there's nothing new there, it's exactly the same as before, and then we would have this, which is exactly the same as before. So not really much has changed here. Oops, dropped my pen. So if we want to actually include our parameter, we need to rewrite this a little bit and actually take this effect into account, because we want to consider the interaction between electrons, and we're not doing it right now. So we have to get creative. And now Griffith, for example, he does this without really explaining much. So you might have, if you come from there, you might have noticed. This is the logic behind what Griffith does. So what we want to do is that we built the wave function, as you can see here, right? This is the logic behind it. We built the wave function for an atom with Z protons. But this is not the Hamiltonian for the atom with Z protons. So let's build that. So what would it look like? Well, it would look like exactly like this, instead of with a Z instead of 2. So, you know, just let's add 0. So add and subtract the same thing. So minus h bar squared over 2m del 1 squared del 2 squared. And now minus e squared over 4 pi epsilon 0. This term I will move and I will replace it with the one that I just added. So this I just added, this entire thing, because now this is this new atom that is basically the hydrogen atom, but with Z protons. And then we have, well, everything else, which is going to be this part and the one that I added. So maybe I'm going to take one extra step to make it super clear. Epsilon 0, 2 R1 plus 2 R2, and then we get plus this other one, so 1 over R1 minus R2, and then minus, actually no, plus, because now we need to add this same thing, so e squared 4 pi epsilon 0. And actually this used to be minus, that's my bad, sorry, this used to be minus. Okay, and this is Z over R1 plus Z over R2. Okay, so now let's, we can simplify this a little bit. So let's see, the first part won't change at all, so minus h bar squared over 2m, this will be the same. And this, of course, will also not change. 4 pi epsilon 0, Z over R1 plus Z over R2. But now everything else we can change a little bit. So we can put both of these things here together. So we can factor e squared 4 pi epsilon 0. And this will give us, so let's see. Actually, we want to put these two together. Sorry, these two. So this would be z minus 2 over r1 plus z minus 2 over r2. And finally, we need to include the interaction term. So e squared 4 pi epsilon 0, 1 r1 minus r2. Okay, so now this is our Hamiltonian. And as we mentioned, this thing right here is simply two hydrogenic atoms, but with Z protons. So for that reason, if we want to find the expectation value of the Hamiltonian, wait, what? I have no idea how I did that. Apparently there's a way to write only straight arrows. I have no idea how. Okay, never mind. So if we want to find the expectation value of the Hamiltonian, right, the energy, well, this is simply 2 times the energy of one of these atoms. So 2 times the energy of these atoms. But what is this energy? So this is basically a hydrogenic atom, but with Z electrons. Well, what is the energy of a hydrogenic atom, but with Z electrons? So let me quickly remind you of the formula for the hydrogenic atom energy. So this was En, this was minus m. This is the same logic as in the previous video, but with Z instead of 2, right? So m divided by 2 h bar, and then E squared 4 pi epsilon 0 squared 1 over n squared. And of course, this is the same as E1 over n squared, right? However, we are in the case n equals 1, so, bye-bye. And what else? Now, the point of this is that this E right here, let me see if there's any way to fix this, actually. Right. So this E comes as before because there's an electron, and actually maybe let's write it like this, and also because there is a proton, or yeah, proton. But the issue is that now we don't have just one proton, we have Z protons. So we have to have a Z here. And since this is squared, we end up with Z squared. So our energy now, in this case with Z protons, is Z squared times the previous energy. Okay, so this is E1. This is, of course, the energy of the hydrogen atom times Z squared. Okay, again, it's the same logic as in the previous video. Now we need this, the expectation value of this right here. So what is that expectation value? Well, let's see. So we get plus E squared 4 pi epsilon 0. And then what else? Then we can factor out Z minus 2. And we are left with the expectation value of 1 over R1 plus the expectation value of 1 over R2. However, there's no difference between both electrons. The expectation value of both is the same. So it's expectation value of 1 over R. There's no difference. They are simply at 2 different places, but it's the same. So this is actually 2 times expectation value of 1 over R. So we can simplify this, multiply by 2, and 1 over R. And in fact, we know what this is because we calculated it in a previous video. And this is 1 over A for the ground state of hydrogen. But this time we don't have, again, it isn't quite hydrogen. This time we have Z protons. So for that reason, A is modified. So this means that now it's not going to be 1 over A, it's going to be 1 over A over Z. So basically Z over A, right? Because A is modified. So everywhere where there is an A, we need to modify this accordingly. Okay. Let's continue. What else? So now let's replace this thing with what we just found. So Z over A. And finally, we need to find the expectation value of this. Fortunately, we did that in the previous video because it was a lot of work. So that is expectation value of VEE is what we called it. And let me double check. What was it that we found it to be last time? Here. So last time we saw that this thing is 5 over 4a e squared 4 pi epsilon 0. And a, of course, now has changed. Last time, a, the Bohr radius, changed to a over 2. But now, it changed to a over z because we have z protons. Last time we considered there to be only 2, or 2. So for that reason, we need to go, so this result is for a over 2, but we need it to be for a over z. So we need to multiply this a by 2 over z. That way, this 2 will cancel out the 1/2 factor from before, and we will get the 1 over z factor. Okay, so we have to multiply this a by 2 over z. So that means multiply a by 2, and the z ends up, whoops, here, so 5z. Okay, cool. Now, we need to consider how to simplify this expression. So just as we did in the same video, actually in the previous video, actually it's the same thing. We have this e squared 4 pi epsilon 0, and actually we have that in both of these cases. So let us, well, where is it? Let me take this value actually. Actually not that part. I want to take this. So I'm just gonna rewrite it. I have no idea how to use this software. Okay, so a, as we saw before, this is 4 pi epsilon 0 h bar squared over m e squared. So if we plug this into this, in both of the instances where it appears, let's see what we get. So we get 2e1 z squared, nothing new there, plus, and now we have 2 times, maybe let's take the z's in front actually, so z minus 2, and now we get 2e squared divided by 4 pi epsilon 0, and then 1 over a. So we get m, yeah. So mass of the electron, I think I use different notations. So this is mass of the electron times the electron squared. Okay, so that's, so mass of the electron squared. Okay, so either call it me squared. Just want to make sure that you got that right. Okay, and then 4 pi epsilon 0 h bar squared. But notice what this thing here is. So let me get rid of all of this. I don't want to get rid of that parentheses. There. So notice that this energy is m over 2h bar squared, and we have h bar squared, and we can take a 2 easily, right? We can just factor out. So basically, e squared 4 pi epsilon 0 squared, we have e squared 4 pi epsilon 0, e squared 4 pi epsilon 0. So we have that, we have this. And then we have m right here, and we have h bar squared right here, and we only need 1/2. So we just multiply by 2 over 2, right? And we take this one. So now all of this will go away, and we are left with E1. And actually, well, we need to put a minus sign in front, of course, right? So E1, but with a minus sign. Minus E1, and there's a 2 here, so 2 times 2 is 4, if I remember correctly. Okay, now the exact same thing we will do to this part. So we get plus 5z over 8. And instead of A, of course, we now have m e squared 4 pi epsilon 0 h bar squared e squared 4 pi epsilon 0. So again, we have one time e squared 4 pi epsilon 0, another time we have m, we have h bar squared, and we only need 1/2. So let's take 1/2 from this 8. So write this 8 as 4 times 2, and we will take this. So now all of this thing is gone, and instead we are left with minus E1. Okay, great. So this thing right here is 2 E1 z squared minus z squared plus, actually there's a 4, I forgot about it. So minus 4 times z squared plus, then we have 8 times z, and all of this times E1. So that looks terrible. So E1 plus 8 E1z, and then we have this amount here. So minus 5z over 4 E1. Now we can simplify this. So add these two together. We get minus 2z squared E1. And then here we can take minimum common denominator. 8 times 4, 32 minus 5. This is 27 over 4 z E1. Okay, so now of course we want to find the minimum possible value. So we take this there, and we derive with respect to our variational parameter, which is z. So derivative here will be quite simple, minus 4z and E1 plus 27 over 4 E1. And this has to be equal to 0. Now, of course, the energies are not 0, so we can simply divide by them. So we are left with z is equal to 27 over 16, which is about 1.69. Okay, so as we can see, the effective amount of protons is less than 2. It is 1.69. So it is between 1 and 2, and that is, of course, because the effect that one electron has on the other. It shields part of the action of the protons. Okay, so this is the value that minimizes it, that minimizes the energy. Well, what is the minimum energy? Well, that's simple. Let's just plug this value in here. So let's see. Minus 2 times this amount squared, so 1.69 squared. And then plus 27 over 4 times 1.69 E1. Let's see. So I'm going to use the full number here. It's actually 1.6875, so I'll use that. This squared times minus 2 times minus 13.6 plus, let's see, open parentheses, 27 times point, and then times minus 13.6. All right, so when we do that, we get about minus 77.5 electron volts. So as we can see, we are now quite close to our expected result. So we are just about 1.5 electron volts away. So using the variational principle, we can see that we can get actually quite close to the energy without having to solve the Schrödinger equation. But of course, we need to come up with a good wave function. Otherwise, simply, there's not really too much we can do, right? If you don't take a good one, your guess won't be good. So all that we did in this problem is that we just had to come up with this wave function. That's actually the only thing that was really difficult. And then we had to rewrite the Hamiltonian. But other than that, it was just a little bit of algebra. So I hope this was useful. If it was, make sure to leave a like on the video, comment and subscribe. And if you got any classmates that might be needing a little bit of help in these topics, make sure to send them the link. So thank you very much for watching. I'll see you in the next video.